Right, so kia ora to this, hopefully just a revision session around the new Level 1 standard on energy, and great to see so many viewers. I'll just bring my comment section up so I can see if there's any comments coming up. Yeah, this is an interesting paper because it's new for 2024, which means there aren't really many past papers to go through. There's the pilot past paper from last year, which I didn't think was very good, so I won't be using it. And there's a couple of NZIP ones you probably did for your derived grade exams. So yeah, there's kind of not much to go on for this, but don't worry. Hopefully by the end of this tutorial, have some sort of idea of what you need to study in the next 2 days. So yeah, any questions or comments, just put them into the chat as I go through the kind of PowerPoint presentation I prepared, which kind of encapsulate the basic points that you need to know, and we'll move on from there. So for those who don't know, I'm Dr. Harves. I'm a physics teacher in Marlborough in New Zealand, and yeah, this is the first time I've done the standard, just like all of you, so we're all learning together. Right, so let's begin the show. Right, so for those who are in the right place, so we're doing NCEA Level 1 Physics Standard AS92047, demonstrating an understanding of energy in a particular system. So the first thing to look at, making sure you're taking notes for this, is what is energy? So energy is essentially the ability to do work. And work done is going to be the energy transferred. And both work, which is the equation of force times distance, and energy are the same. So when you're doing work, you're applying a force over a distance, you are creating energy, and also requires energy to do work, to push a force. So for example, to lift an apple, as we see here, this green apple up here, upwards by 1 meter requires 1 joule of energy. So that's what energy is. So this is actually quite an intense slide. But it just illustrates, hopefully, some of the forms of energy that you've studied in the classroom this year. So we have thermal energy, which is a particular subsection of this unit, and it's an object related to its temperature. It's also called heat energy. And light energy is in the form of visible electromagnetic radiation. We don't really go into much depth around that in terms of level 1 physics, but if you move on to level 2 and level 3 physics, then you learn more about electromagnetic radiation. Then we have electrical energy, which is also very important in this standard, and it is the energy transferred by an electric current, and we'll touch on that later in this webinar today. Then we have sound energy, which I was working on with my year 10s today, and it's energy in the form of a sound wave. There's kinetic energy, which is a form of mechanical energy, which is probably the first thing you looked at when you looked at this standard with your teacher, and it's the energy of moving, and there's a special equation with that, which you have to be familiar with, though you do get the equations in the exam, which is quite useful. And the reason why that equation is important is that second point, that kinetic energy increases with object speed. And when we look at that equation, we will see why. Then we have chemical energy, and it's the energy released during chemical reactions. So when you have a hamburger at McDonald's, that is the energy that's released in order to, well, there's a question here from Sav. I'll just post it on there, show, yep. Is thermal energy also energy due to the particles of a substance arrangement, or is it only the movement? Yeah, so that's the point. So thermal energy, the heat energy, is going to be the energy of basically the energy of the bonds between the particles. You don't have to go much into depth around atoms, but yes, that's what it is. It's basically year 11, it's more about the particles rather than calling them atoms. We'll look at that more in level 2 and level 3. So yes, that's thermal energy. Okay, so we'll just hide that. So thank you, Seb, for that question. Okay. Yeah, so chemical energy, also important because that's where the energy from batteries comes from. And we have nuclear energy, which again is more touched on in level 2 and level 3 physics. But the important one we look at is nuclear fusion, which is the sun's energy. Then we have potential energy, also part of the mechanical energy. And again, there's an equation for that, which you have to be familiar with, because chances are you will be asked to use that equation in the exam. And a special one is that gravitational potential energy. That's the most important question. Again, we'll touch on that later in the webinar. And then finally, something you could touch on is the elastic potential energy, unlikely to be used in level 1 physics, the equation at least, but it's something you have to be aware of, but that's more in level 2 physics. Right. So as I mentioned in the previous slide, there's kinetic and gravitational potential energy. So you have to be familiar with these equations and be able to rearrange them to get variables, especially in the merit and excellence questions. Achieves, usually you just use the equation straight from the formula sheet. So kinetic energy is essentially the energy of an object due to its moving. So when you're moving, you have kinetic energy, and the equation is going to be related to the object's mass and velocity. And the equation that you have to be familiar with, that you do in the exam, is kinetic energy equals half the mass times the speed squared. That's why speed is important, because when the speed increases, say doubles, that means the kinetic energy is going to quadruple, because it's that squared function. And the other important equation in mechanical energy is gravitational potential energy, so GPE, and that's the energy an object possesses due to its position relative to the Earth's gravitational field, okay, due to gravity. So in that previous example with the apple in the previous slide, that had gravitational potential energy in the apple tree, and then it fell on Newton's head, and then that got transferred from gravitational potential energy into kinetic energy. And that equation is mass times gravitational field strength times the height. And you'll be given the gravitational field strength in the exam. For level 1, that's 10 meters per second, or 10 newtons per kilogram. Okay, and as I mentioned, with that apple, as the gravitational potential energy of the apple is transformed to kinetic energy as it moves. So at the highest point, gravitational potential energy, when it's in that tree, is at a maximum, and the kinetic energy is 0. As it falls, the gravitational potential energy increases while the kinetic energy increases. And the reason I have that last paragraph is due to an important concept around energy transfers and the concept of conservation of energy, the law of conservation of energy. So usually the merit questions and excellence questions probably are going to be testing you on the law of conservation of energy. So energy cannot be created or destroyed. It can only be transformed into another form. Okay, so in the apple example, there's no, that gravitational potential is not being destroyed. It's just being transformed into another form, kinetic energy. And as I've mentioned, that is the law of conservation of energy. So the total energy of the system. Oh, does the apple have, okay, I'll just put that up there. Here we go. Does the apple have any kinetic energy just before it hits the ground? Yes, that's when it is at its maximum. The quirk of the questions is that it's always reading the questions just before it hits the ground, because obviously once it hits the ground, it ain't moving. So then it's got no kinetic energy. So it's usually just before it hits the ground. That's what the merit and excellence questions will focus on. And is GPE the same everywhere on Earth? For level 1 physics, yes, it is, because the gravitational field strength will be given as your 10 newtons per kilogram, even though in reality it does actually change. So in Blenheim, in lab 1, it's about 9.83, but in the exam you just say it's 10. Okay. Okay. Is energy always conserved in every system? Only in a closed system, and that's the only system that you have to worry about. Okay, cool. There we go. What's the other questions there? Does it have any gravitational potential energy? Yeah, so the way the question will work, it'll just be just before it drops. So it's going to be essentially 0, about a millimeter above the ground, because the height will be minuscule. So yeah, For the purposes of level 1 physics, it will essentially be 0. Okay. So the energy cannot be created or destroyed, be transformed. This is what my teacher said. Yeah, that's it. That is the law of conservation of energy. Lukey dookie, you've got it completely correct. And if you state that in the exam, I'm sure the examiner is going to be loving that. Okay. So yeah, in terms of energy can be created or destroyed, can only change form. So yeah, Lukey dookie just mentioned. This is known as the law of conservation of energy. So yeah, the total energy stays the same. So looking at an Apple example, the total energy is say 1, and say at the start it would be 1 for gravitational potential energy and 0 for kinetic energy. And just before it hits the ground, for all intents and purposes, it'll be kinetic energy will be 1 and gravitational potential energy will be 0. But the total energy of the system will be 1 joule. Yeah, so energy can be transferred. That's transforming, but it also can be transferred through work. Okay, so that's again what we're discussing. So it can be transferred between objects using a force, because work equals force times distance. Heating is basically where the thermal energy moves from a hot object to a cold object. So therefore, the temperatures of the two objects begin to be the same. And then electricity, energy is transferred through sources like batteries and components like light bulbs. For level 1, it's only a small range of components you have to focus on, probably 2 or 3. And then waves, which is more about level 2 and level 3 physics, energy is transferred through sound and light. Okay, another important topic or subtopic is energy LOL charts. So LOL is just in what they look like. So energy bar charts are visual tools. So for those who did the derived grade exams through the NCEA exams, you probably would have been asked to draw a few. Okay, it just basically is a way to illustrate how energy transforms without being created or transformed. And Worm loves those charts by the looks of things. So in order to do an LOL chart, you have to identify the system. Okay, that's the object you're analyzing. So for example, for the Apple system, it's just the apple. Okay, identify the initial state. So in that particular case, the initial state is the apple is in the tree. And then identify the final state, the apple is just dropped before the ground. And then determine what's changed. So it's now the transformation of gravitational potential energy at a maximum at the start and kinetic energy at a maximum at the end. And then you just draw the two charts. So you've got L is the initial state, the O is the system in the middle, and then the second L is the final state. So in the Apple example, the initial state is all GPE, and then the final state is the all kinetic energy. Zai's got a question there. What should the main key idea that I should study before there? Here, the main key idea. Well, I think conservation of energy is pretty good, but there are quite a number of key ideas to actually look at in terms of the topic. There's no one key idea that would just make you pass. There's a whole number of key ideas, unfortunately. Okay. Right. So then. So once you've drawn the chart, you add the energy transfer processes if applicable. So, for example, if work's going to the system, so what's his name? Sir Isaac Newton therefore lifts the apple up, then it's giving Sir Isaac's giving it work. So then that gets transformed or transferred into transferred into gravitational potential energy. Okay, excellent. Well, that's a big slide as well. So that's the focus of the conservation of energy. So that's quite a big slide. So it's just reinforcing what Lukey dookie said, the idea that energy cannot be created nor destroyed. It can only be transferred or transformed into another form. But the total energy of the system stays the same. Okay, so I'll just outline the Apple example there. In terms of GPE at the start is a maximum, kinetic energy is a minimum, and then when the apple falls, the kinetic energy is a maximum and the gravitational potential energy becomes a minimum, even though the total energy stays the same in the system. Okay, and LOL charts, which we just looked at in the previous slide. Oh, here we go. Right. Right. Could I pass the exam without any actual equations and just explain stuff instead? Okay, so they've slightly changed the marking schemes now in physics. So the EA questions tend to be the explain part. But the problem is that in physics, we tend to mark a little bit harder than the other sciences. We have top-down marking, which means that if you don't get the earlier points, you don't get the excellent points. So you actually have to have a deeper understanding of the physics if you want to get those excellence points. So sorry, Worm, you can't just do no calculations and just explain stuff. You actually also have to be able to apply the equations. Sad. But yeah, that's one of the quirks of the physics. Yeah. Yeah. So in terms of conservation of energy, you've also got things like friction, and that means you also get energy. Yeah. So Callum, that's why you got marked down so much in the mock exam. Yeah, that's the thing. You have to have the underlying knowledge, the achieve part, before you get the excellence. Yeah. So in the real world, we usually have something called wasted energy, usually in the form of heat caused by friction, for example. So as that fell, that apple, obviously it's interacting with the air particles, so it's going to have friction. So some of that energy will be lost as heat. Okay, and that's what I'm just touching on this slide. So useful and wasteful energy, which links into efficiency later. So useful energy is the energy transferred to where it's needed in the desired form. Oh, please. Other forms of energy are considered wasted energy. Okay, so usually in the context of level 1 physics, the wasted energy is usually in the form of heat, which makes the surroundings warmer. So chances are you might get a question around maybe some friction occurring. So it means that some energy is lost in heat. And that's probably going to be in your merit excellence level questions. And the reason why I'm mentioning this wasted and useful, useful and useless energy is the idea of energy efficiency. Okay, and it's basically how well a device converts the energy it wants to a useful form. So the classic example is a light bulb. So a light bulb, an inefficient light bulb, converts most of its energy, electrical energy, into heat energy and not light energy. It's about 10% light to 90% heat, whereas a efficient light bulb will do the opposite. Okay, and there's an equation with that. The efficiency can be greater than 1, because basically 1 is 100% efficiency. So efficiency is the useful energy going in divided by the total energy going in. No, sorry, I'll say that again. The useful energy going out, yeah, and divided by the total energy going in, and the percentage efficiency, basically multiply that number by 100. And the higher the percentage, the more efficient the device. So there could potentially be a question on basically efficient light bulbs is a classic one, which kind of tests your understanding of efficiency. Okay, so you might also be asked more in the merit excellence questions. Okay, I've got an inefficient system. How can I make it more efficient? So you can reduce heat loss by, say, if it's a machine, by using lubricants to minimize friction. I can hear my class of boys now. Oh, geez. Decreasing electrical resistance in circuits, using streamlined shapes to reduce air resistance, or reducing sound loss by, say, tightening loose parts on machinery. And that's ways that you can improve efficiency. So that's probably more your deeper thinking, your merit, and your excellence questions. So that brings us to, so yes, the formula will be provided in the test for, not the efficiency one. The efficiency one will not be, but the kinetic energy, gravitational potential energy will be, yes. So power, which is also used in the other parts of the standard around electrical and thermal energy, is given by 2 equations. So either power equals the work done, or work done by the time taken, or the energy of that time taken as well. Okay, so power is measured in watts, work is measured in joules, just like energy is measured in joules, and time, of course, is in seconds. So remember, with these questions, you need to convert, say, if you're given time in minutes, to time back in seconds in order for the equation to work. And so basically, 1 watt is equivalent to 1 joule per second. And power, as I mentioned, also can be change in energy divided by the change in time. So the question, let's put that up there. Okay, so Zai has asked, will P equals V times I be given in the exam? You're lucky, unlike the efficiency one, which might not be. Yes, you'll be given that exam, that equation in the exam. Good question. Okay, so that's basically the first kind of subtopic in this standard, which is more around mechanical energy. And then we have the next kind of third of the topic, which will be heat transfer. So thermal or heat energy flows from hot regions to cold regions through 3 processes. So there's either conduction, which transfers the thermal energy through solids. Oh, right. So Lukey Dookie asks, how many questions do I need to get correct to get achieved? The problem with that is it will depend on the rest of the country. And if you kind of aim to get how many questions to get right, then you're probably not on the right track of thinking. Yeah. So classically, it's 8 achievement points, but you don't know what the achievement points are. So I would not try and play that game. Try and aim for the sky, aim for high excellence. And if you make a few mistakes, you might get a merit. Whereas if you try and aim for achieved, you step up somewhere, then you end up getting it unachieved. So try aim high rather than trying to aim low. Okay. So that was conduction. Okay, so that's between solids and metals are good conductors. Gases are good conductors, whereas gases are poor conductors because the particles are not quite close together. Okay. And a vacuum does not allow conduction because there's nothing in a vacuum. There's nothing for thermal energy to pass to. So think of it like particles jiggling. Okay, it's easier to knock against somebody who's close by rather than way off in the distance. And that's kind of the way it works. Heat transfer is quite fast by conduction because of that. Okay, then we have convection. So that's transfer through fluids. So when I say fluids, that's going to be liquids and gases. And basically the upward movement of water into less dense regions. And this does not occur in solids or a vacuum either, because convection only happens in liquids and gases. Then we have radiation. So it's a transfer of energy by infrared radiation waves. And it's the only one that can transfer through a vacuum. Okay, because it's basically electromagnetic radiation, so it doesn't need particles to transfer that energy. And it travels pretty fast at the speed of light, 3 times 10 to the 8 meters per second. And gases are more transparent to radiation than liquids, and those are less than solids because there's lots of gaps between gases. Okay. And I think probably, yeah, I'm probably right. You're probably going to have to sell your soul to get an E8, but you never know. Right, so mentioned previously thermal radiation. So all objects above absolute zero, which is minus 273.15 degrees Celsius, emit radiation. So you're emitting radiation right now. And hotter objects emit more radiation. And dark and rough surfaces emit and absorb radiation better than bright and polished surfaces. And bright and polished surfaces reflect radiation better than dark and rough surfaces. Now, there might also be a question in the exam, just theorizing, about insulation, for example. So that's the reduction of thermal radiation and thermal heat transfer. And the way insulation reduces thermal transfer, it kind of separates the particles. So there's less energy being transferred between those particles over time. Okay, so that's that part. And then we have specific heat capacity. Okay, so specific heat capacity, I recommend you revise that definition, because that's a very easy achieve point to get. and it's the energy required to raise the temperature of 1 kilogram of substance by 1 degree Celsius. Okay, so we use degrees Celsius in level 1. That's more than acceptable. As you move into level 2 and level 3, we'll have something called Kelvin, but that's for next year, not for this year. Don't worry about that. And it's a measure of how much energy a material can store. Okay, so water, it's a classic. It's got a high specific heat capacity, meaning it can absorb lots of energy without becoming very hot. It requires lots of energy to heat up water. And the equation, which you'll be given in the exam, if you're curious, is E equals mc delta T. The mass multiplied by the specific heat capacity multiplied by the temperature change gives the amount of thermal energy. Okay, it's possible for merit and excellence. You might be asked to rearrange it to find a temperature change or a specific heat capacity or a mass based on an energy or the other variables. Okay, so again, rearranging equations is important for the standard, especially in the excellence and merit questions. And I guess before we move on, we have to look at the difference between thermal energy and temperature. So temperature is the measure of the average kinetic energy of all the particles in a substance, whereas thermal energy is going to be the total amount of energy. Okay, so even though something might have a high temperature, it might have a low thermal energy if there's not much of it. So think of a swimming pool at 20 degrees Celsius, has a lot more thermal energy. A cup of tea with 100 degrees Celsius is a lot more water. Okay, so the question, I've also got Midglosky as well. Okay, so let's look at Lukey's first. What is delta T? So delta is change and T is temperature. So it's going to be the change in temperature. So in an exam question, you might say the piece of metal increased from 20 degrees Celsius to 30 degrees Celsius. So therefore, the delta T is going to be 30 minus 20 or 10 degrees Celsius. Okay, that's delta T. And indeed, air is a great insulator and explains that question, which was asked from Midglosky. What's a great example of insulation? Air. That's why we wear clothes, because the air is trapped between the layers of clothes, which helps insulate us. Exactly. Okay, so nearly done. So in terms of latent heat is another example. So latent heat is quite a difficult context. Oh yeah, that's a good point there, made by Kamalatics. So uppercase T is temperature in degrees Celsius, and lowercase t is time in seconds. Yes, in physics, we use a whole range of symbols. And that's correct. Uppercase T is temperature, and lowercase t is in time. Correct. Very, very good. Right, so latent heat, that's kind of a difficult concept possibly to get your head around, but latent heat is the energy required to change the state of a substance without changing its temperature. Okay, and what the reason why it doesn't change in temperature, because remember, temperature is the measure of the kinetic energy of the system or of the substance. Okay, so that means if there's no change in temperature, then the particles aren't moving around. Okay, the reason why is the energy is not being used to actually move the particles around. It's actually being used to break the bonds between the particles during the states, changes of state from liquid to gas, or say solid to liquid. And the specific latent heat is the energy needed to change the state of 1 kilogram of a substance without changing its temperature. And there's two specific ones, and these values will be given to you in the exam, so you have to worry about remembering them. So latent heat of fusion is the energy required to melt 1 kilogram of solid of a melting point. So it's specific to the particular solid, whereas latent heat of vaporization is the energy required to vaporize 1 kilogram of a liquid at its boiling point. And I haven't put the equation down, but the equation is energy thermal equals the mass times the latent heat. And it depends if it's a solid or a liquid, if it's going to be using latent heat fusion or latent heat of vaporization. But you can kind of work that out because the question is going to give you one of those values. Okay, right, so it's got a question here from RoboJam247. Is glass a good conductor for heat? It's more of a liquidy. It's kind of a poor conductor, to be honest, glass. There's Metals are probably the best conductor, and metals are probably going to be the example you're going to be used in the exam. So in terms of Adaya Vishnakuma, do they give formulas? Yes, they do have those two formulas. Those two formulas will be given in the exam, so you don't have to worry about memorizing them, which is great. Okay, so we've gone through mechanical energy. We've now raced our way through thermal energy, and then we are going to look at electrical circuits, but first he's got a question, so I'll just go through that one. Okay, so Maggie asks, what is the difference between latent heat and specific latent heat? Latent heat is basically the generic term, whereas so latent heat is the amount of energy required to break the bonds between particles, whereas specific latent heat is specific to a particular substance. So every different substance has a different latent heat depending what it is, because the strength of the bonds between those particles are different. So waters have a different specific latent heat than, say, iron or carbon dioxide. Right. So I'll just hide that comment. There we go. Right. Okay. So Mando Clips has possibly some questions, but I'll continue moving on. Right, so electrical circuits, next, or the last subtopic. So we're near the end of this rush through the standard. But electrical charge flows through a circuit only if the circuit is closed, okay, and also if there is a battery, a source of electrical potential difference. And current is the flow of electrical charge, and the high rate of charge means a higher current. And finally, resistance is second to last. Resistance is the opposition to current flow. All components have resistance. And so voltage is the potential difference between 2 points in the circuit, and it's basically the push that drives a circuit, the oomph, as you might say. So the question there. So Miglowski, don't worry. As soon as that's over, it's all recorded on YouTube. You can watch it again. It's up there for eternity. Oh dear. Anyway. Okay, so in terms of circuits, there's two types of circuits you'll focus on: series and parallel circuits. So a series circuits, the Christmas tree lights, since it's going to be Christmas. Oh, here we go. Got a question here. Would a high current and low resistor generate more heat, or a low current and high resistance? So actually, that was a question my two budding students who turned up to the tutorial this morning actually went through. So basically, a low current, high resistance is more likely to generate more heat. Yeah, so that's essentially how a tungsten filament lamp works. It's basically a high resistance and a very thin filament. So a lot of it gets turned into heat, which causes the metal to glow, and that causes the light. Right. So back to this. So your series circuits, components are connected end to end, forming a single path for current. The current is the same throughout the circuit. The total resistance is the sum of all the resistances, and the potential difference, or voltage, is the sum is shared across the components. And then and that's basically your Christmas light. So if one Christmas light goes out, then it's it for the entire circuit because it's going all through one point. Whereas parallel circuits, which tend to be what's used in the circuitry in your house, the components are connected in separate branches, which means the current is shared between those branches, and the voltage is the same across each branch. So the total resistance is less than the smallest individual resistance. Okay, we got another question going. Check. What has more resistance out of a two resistor in parallel? One on each branch or two in the circuit? I'm trying to get my head around that question. So two in a series circuit. Well, actually depends on what the resistances are, but if you have two resistors in parallel, it's going to be less overall resistance than two in series, depending on the size of the resistance. But yeah, because basically the current is shared, so it gives the electricity options in the parallel circuit. Yeah, so all resistors are equal resistance. So if that's the case, a parallel circuit will have lower resistance. And you look at that in more detail in level 2 physics. So it's just the overall quantitative rather than qualitative values that you worry about in level 1. And remember, the standard is focusing more on energy. So the idea of resistance and calculating resistance is very unlikely to be in the standard, or the exam is more about the energy associated. Yeah, so a lot of questions being answered. So which one will generate more heat? The one with more resistance. Next question. So will the exam require us to remember all the electrical symbols? Well, for those who follow my YouTube channel, all the electrical symbols you have to know are part of the Kung Fu lesson. There's not many. It's basically a battery, but chances and a lamp. But chances are you'll actually be given that in the exam, because again, we're not going to be assessing your knowledge of circuit symbols. We're testing your knowledge of energy. Okay. Right, Nick, moving on. What's happened? Why is it? Why is it stopped? Was that it? Oh, that's it. Yes. Brilliant. I think that might be my PowerPoint. Yeah, that's actually the end of my PowerPoint. Brilliant. Have I frozen? Oh, no, that's no good. Hey. Why stopped? Oh, here. What? Oh, no. Okay, can you hear me now? I took myself off the stage. That probably wasn't the smartest thing. Can you hear me now? He's back. Yes, I'm back. Right, so now I've got to go through all of those things again. Okay, so that's fine. What do we got? Okay, so to answer that question there, no, you don't have to do RoboJam. That's for level 2, so don't worry about sine theta. And the SciPad question, yeah, if you follow the SciPad, you're all good to go. Lots of content on SciPad, which is pretty close to it. Yep. Yeah, just saying my MBC computer kind of just went rogue. Yeah. So I've got a few slides left. So we looked at power in terms of mechanical energy, and we'll just look at electrical power now. So, and that was already mentioned previously right at the start. that an equation called power equals current times voltage would turn up. Indeed, it will. But remember that power is also change in energy over change in time and work over time. Both equations you should be given in the exam. So you've got to be careful about what equation you're using. It's also measured in watts. That doesn't matter if you're doing it in mechanical energy or electrical energy. It's all in watts. And yeah, so power also equals current times voltage. So you might be given a merit or an excellent question where you have to calculate the power of a series or parallel circuit and also look possibly at the brightness of those bulbs. Whereas in a parallel circuit should be bright in the series because the voltage is going to be the same all the way throughout. So you're going to get lots more energy being transferred to the bulb in a parallel circuit. Yeah, that's important. Yeah, so, I've already mentioned this. Okay, yeah, so power's in the series circuit. So in a series circuit, current flows from each component. So if we plug in the equation power equals current times voltage, we'll see it'll end up having a lower power output compared to if it was connected. It's a question there from Arwen. Is the brightness to do voltage or current or both? So yeah, so it's going to be in that paragraph there. Since the power is the product of the current and the voltage, each component in a series circuit will have lower power because they are connected individually to the voltage. So you're sharing the voltage basically. Okay, and the more components you add, the more the voltage goes down and the more the current decreases as well because the resistance is also going to be increasing. Okay, so that kind of that paragraph on that slide is actually answering that question. Yeah. What pages? In terms of the SciPad, it had everything. Yeah, so good luck with that. So is the SciPad practice exam similar in content to the exam? Well, we haven't seen the exam. We don't know what's going to actually be in it. We're only kind of guessing based on what we've taught. But I would suggest that the SciPad practice exam probably will be very close to it. The pilots that they used last year, it was a bit higgledy-piggledy, the scaffolding from achieved merit to excellence. And the last question was completely rubbish. Whereas the NCEA ones, if you've done that for your arrive grade exams, are probably closer to the mark in terms of scaffolding from achieved merit to excellence and expectations about what's required for those particular, for achieved merit and excellence. Is an equation for resistance in the exam? Again, thing is, we're not assessing electricity. We're assessing electrical energy. So you won't be asked to calculate resistance because that's not what we're assessing. We're assessing energy. The only one I'd suggest you look at is voltage equals current times resistance, which is Ohm's law, which is something you can use to answer questions around power in series circuit. Because if the voltage of the battery stays the same, if you increase the resistance by adding more components, say in a series circuit, then you're going to be decreasing the current. So that means the brightness is going to go down as well. Yeah, that's what we have here. So a decrease in power is evident in the dimming of the light because your resistance is going up, your current's going down. And then finally, add it to the end, power in a parallel circuit. So in a parallel circuit, the voltage across each component is the same, but now you're sharing it between the branches. But since each component in a parallel circuit receives the full voltage from the battery, it will have a higher power output compared to the components in a series circuit. So that's why you're going to have brighter lights in the house rather than the Christmas tree. Okay, because you actually, the more components you add, in parallel, the resistance goes down. And this increase in power you can see because you're going to get brighter lights. That's usually a classic question in this kind of exams. There we go. We are at the end of my slideshow. So any particular questions, specific questions, I'm ready to answer for the next, say, 10 minutes. And then I've got to prepare my lessons tomorrow. But yeah, so great audience. Thank you for your questions. But yeah, any more questions? Otherwise, we will call it an evening and you can get back to studying. Any questions about physics? Okay, right, so question asked, how important will the initial section be? So the way I envisage it is what I'll do is I'll have question 1 will be about mechanical energy. Question 2 will be about heat or electrical energy. And question 3 will be about heat or electrical energy. So I reckon there'll be a complete question on electricity. So you have to know pretty much all the sections in order to pass. Would you say that last year's paper is similar to this year's exam? I hope not, because I don't think it was very well done. I hope there's a bit of an improvement. Right. Oh, on that. There we go. So Abigail's asking, is the latent heat of vaporization? Yeah, it's called the latent heat of vaporization. So it's the energy required to go from a liquid to a gas to form a vapor. So yeah. And also conversely, it's the negative number because you're taking energy out of the system. It's also the negative energy is going from a gas back into a liquid. We didn't quite touch on that because there's a lot to go through, but yeah. There's a question in the side pad where the answer said steam. I don't know what the question is, so it's a bit difficult. I think 115 degrees Celsius seems a lot more sensible than 1,000 degrees Celsius. You can't necessarily always trust SciPad. 1,000 seems cray-cray. So yeah, I'll go with 115. Can you use the old level 1 papers? Yeah, the level 1 papers that I'd probably look at are the old energy standard, but you have to be careful because there's some content that's not being covered, so you might not need to do it. But things around specific heat capacity, for example, and latent heat are definitely going to be in this exam. So yeah, using those kind of things and energy transfer, for example. So yeah, I think, Luke, that would be a good idea. Okay. Why does latent heat of vaporization take longer than latent heat of fusion? I don't think it does. In fact, I don't know what that question actually asks. Why does the latent heat of vaporization? Why does melting take longer than freezing? I would challenge that. I'm not sure that that's correct. Yeah, I don't think that makes sense. Okay, right. So, is current the rate of flow of charges, or just the flow of charges around? Well, I guess when you're asking, the flow is essentially the rate. It's the amount of charges passing by per second. So I would say it's just the rate of, yeah, the flow is essentially the rate anyway. So it's like a tautology. I'll say the flow of charges, in this case electrons, around a circuit. Okay. The difference between conduction and convection. So conduction is heat transfer with solids, whereas convection is heat transfer with fluids. So heat transfer in liquids and gases. So there we go. Okay, what's this say? What does it mean when gases are more transparent to radiation? So basically, it's easier for radiation to pass through a gas, like our atmosphere, than it is to pass through me or a solid, or you for that matter, because you're going to absorb that radiation, whereas the chances are the radiation is not going to hit a particle of the atmosphere because they're so well separated. So that's what it means when it says it's transparent to radiation. The heating curve shows melting. Well, the thing is with that one, it depends on the substance. Every heating curve is different. I guess you can argue that the steepness, because what you've got, yeah, so I got that now. So for fusion, the particles are really close together. So that means that they're really attracted to each other. So it requires a lot more energy to break that bond between particles. Whereas when you've got a liquid and you want to separate it out back into gas, that's going to require less energy. So it's going to be a lot faster because the strength of the interparticle bonds are going to be less than the particle bonds between the solid. There we go. That makes sense then. Yeah. Okay, just going through a few more questions. If we have a higher voltage in a bulb, would that make it glow brighter than a bulb with lower voltage? Yeah, because what you've got, power equals voltage times current. So assuming the current's the same or similar, then it's going to glow the bulb is going to basically glow brighter because there's more voltage passing through it. Because voltage is going to be the joules per coulomb or per charge. So if you've got more joules per charge, that means that you're going to have a lot more of the electrical energy being transferred into light energy if it's going to have more joules, more voltage. In the energy bar chart, what do we include in the system? Well, that's actually up to you because it depends on the system. There's no one firm rule. So, for example, with the apple, it's only the apple. As, for example, if you've got a person lifting up the apple, then the person is also going to be in the system because they're providing work to the apple to lift it up to get gravitational energy. Is it not faster to melt than evaporate? Well, that's an experiment for you, isn't it? Yeah. Because it requires more energy to melt than it does to evaporate because the particles are pretty close together. So, yeah. Also depends on the substance as well. You can't make these claims. I mean, yes, for water, be a case in point. Okay, okay, all right. How did I? Oh, here we go. I've got to hide that one. I accidentally. Good joke, but yeah. Right. Okay, so a few more minutes. Oh, you go. When calculating, why do we have to do heating, then change, state change, to then keep repeating to what we want? Wait there. Why do we have to do heating, C, and then change, state change, L? I guess it depends what the question is asking, isn't it? Because if it's either going to be your excellence questions, so it's possible that you have to work out the amount of energy that you need to start actually doing melting or changing the state. So without knowing the actual question, it's a bit more of a challenge to actually answer that question off the bat on a YouTube video. Yeah, probably need to see the question. Here we go. Going from solid to gas. So when you're going from so to go from solid to gas, you're going to have two phase changes because it's going to go from solid to liquid. So you've got to work out the energy required to get it to liquid, and then you're going to have to work out the energy required to get it from liquid up into gas. But also, in order to get to the gas, it has to get up to the melting point. So that requires an addition of energy to give it its temperature. That's probably an excellence level question. Yeah, that's why you have to do it that way, because it requires energy to get it up to from the boiling the melting point up to the boiling point. Right. Will they ask questions that require formula that haven't been provided in the formula sheet? The only thing I'm thinking of is possibly something around efficiency, which I've already gone through the equation there. So that's your useful energy divided by the total energy divided by the time multiplied by 100 over 1. But usually, actually looking at the previous exams, they would have given you the efficiency anyway. I'll say the reaction is, or the system is 0.3% efficient or 30% efficient. So you just got to look at the total energy and multiply that by 0.3 in order to get that 30% efficiency. Cool. Okay, guys, it's been fun. All the best for your examination. And okay, one last quick. Oh, it's more questions. Okay, I'll get to 8. Okay, 8 o'clock. Okay, here we go. Right, so will we have to turn J into joules or megajoules? Yes, you will have to, because the equations work around it being joules. So for megajoules, you have to multiply it by 1,000, and kilo you have to multiply megajoules by 1,000,000, and kilojoules is by 1,000. Okay, right. So don't worry. So explain how the process of convection eventually transfers thermal energy to all the water in a kettle. Well, it does, because you've got the element as well. It depends how it's heated. But I guess convection, okay, so the way that works, the whole heat transfer, is the idea that as particles get warmer, they begin to spread out and become lighter. They go up, they cool down, they begin to compress, and then they're back down again. And that means that it's a convection current, which means the temperature basically is the same all through the kettle. Yeah. Will they tell us the equation to change? Sadly, Gwen, no. You're going to have to remember it. Yeah. You have to know that 1,000 kilojoules is, 1,000 joules is a kilojoule. Yeah, as mentioned by Bob and Parametrics. What would be a good way to explain convection currents, and how does the insulator keep something cool or hot? It's okay, right. So convection currents. So I'd link that to particles separating, becoming lighter, rising. As they cool down, they will begin to condense. It goes together, become denser, and then they fall down. That's probably the best way to do that. And how an insulator keeps something cool or hot. Well, that's your 3 different heat transfer. So conduction, convection, and radiation. So radiation, you've basically got a silver surface, so it's going to reflect the heat radiation back into the component if it's going to keep it hot. Okay, whereas convection and conduction, you're looking at the vacuum, the gap between the two. Keeps it cool or hot because the heat can't be transferred from the inside to the outside. Yeah. No, so basically when you're doing the calculation, you have the big number in your calculator, and then when you get the answer out, you can change it back into megajoules or kilojoules. So if you have like 1,000,000 joules, then that's going to be megajoules. Yeah. So that's when you're right at the end, you change it back. Otherwise, it's using the whole page with lots of zeros. But yeah. Cool. Well, I hope that was helpful. I'll probably end the questions now. Yep. So, as I said, all the best for the exam. Okay. Remember to failure to prepare is preparing to fail. So prepare well, do lots of limited number of previous exam questions, writing out the notes again, highlighting, making mind maps, asking questions of your friends, see if they understand. That's the most effective way to revise. So, yeah, all the best, and I will see what the paper's like on Thursday. Ka kite anō.